That should keep it stable, and it is recording. All right, so you have a quiz on Wednesday on chapters 8 through 10. So why don't we start out with any questions on chapters 8 through 10?
84 in chapter 8.
So chapter 8, which problem?
84.
84. Friction is needed for a car rounding a curve, but if the road is banked, friction may not be required at all. What supplies it? All right. So a banked curve just means that, so if we have an overhead view and fading markers. Overhead view of a curve, car going that way. From the back end view, banked just means that it's at an angle. Right, so overhead and back view. Let's start out with the force diagram. What are the forces acting on the car?
Weight. Normal.
Okay, I think those are the two. So we have weight acting down and normal acting that way. Since they are making the claim that if you bank it just right, you can avoid friction. Well, first off, what is the direction of acceleration? I guess first off was the force diagram. So secondly, what's the direction of acceleration? Down, is it straight down?
No, like down the hill.
Down, that way?
Yeah.
If the car were just sitting there, yes, but the car's moving, so it changes the direction of acceleration. For something traveling in a circle, what is the direction of acceleration?
In the direction of motion?
No.
In the direction of motion?
You mean, so the acceleration would be that way? Or that way? No, we are going to assume that it's traveling at a constant speed.
Oh, would it be inward? Like towards the center of the curve?
Yes. For something traveling in a circular motion, the acceleration is towards the center, which is that way. That's the acceleration. So when we're on here, so the back end view, which way is the center of the circle?
Outwards, like towards the.
That way?
No, that way.
That way. No.
Right, it's circular.
It is.
Would it be toward the board? Would it be toward the board?
That way?
Yeah. It'll be that way.
If the acceleration were, if it were changing speed, then you could make an argument that there was something going in that direction. But since all it's doing is changing direction, the acceleration is towards the center of the circle. And which way were you pointing? That way? Yeah, that way. The car is traveling in a circle.
It's going like this. Oh, okay.
This is back view.
I thought it was going downhill. I see.
So it's traveling in a circle like this. If the acceleration were that way, as in classic box on ramp, then that means the car is accelerating around in a loop like that, but it's not. It's traveling in a circle like this. So acceleration is in that direction. Well, I have two forces here. Which force has some component in that direction?
Normal.
So it is the horizontal component of the normal force. So if, well, let's just add these two vectors together. So I have normal force going this way, and I have weight going down. So my resultant is a vector from where I started to where I ended. That's the total force right there. So if I'm at an angle so that my total force is in the same direction as acceleration, then that's my centripetal force right there. And it is possible. And then with trig, you can figure out what the angle actually needs to be for a particular speed. But it's the horizontal component of the normal force which provides the centripetal force. I assume that made your day just a little bit brighter. Make sure I answered the question. What supplies the needed centripetal force? It's the horizontal component. Consider vector components of the normal force on the car. Yeah. So I'm pretty sure we answered the question. Any other questions on this one, problem 84 from chapter 8? Okay, other questions from chapters 8 through 10? All right. Not quite sure how far over. So it looks like in between the 1 and 2. All right. This one's over here. There's some new markers around here somewhere. Oh, there they are. And potentially some of these. Let's see how well this one does. All right. So, based upon your previous knowledge, other science classes you've taken, and just general life, what goes into an atom? Those are the three big ones. All right. So electrons. What can you tell me about any of these three things? Okay, what a charge of what?
Negative charge on the electron and positive on the proton.
Say it like you mean it.
I always get those two confused for some reason. I don't know why.
Oh, so far so good.
And the neutrons are neutral.
All right. So because of that, we need a shorthand. Of course, we need a shorthand notation to write the stuff down. So electrons will do an E with a negative sign up as a superscript there. And that's the symbol for an electron. Protons would be a P with a positive sign. And then neutrons in with a little 0 right there, indicate that it's neutral. All right, so electrons are negative, protons positive. I guess proton and positive both start with P, as if you need some sort of memory trick. Neutron and neutral. And electrons, negative, yeah, it's the other one. All right, so what else can you tell me? Pardon?
It's a nucleus.
Ah, what goes into a nucleus?
Is it the neutrons? No. Protons and neutrons.
Yeah. So we have this nucleus here, but how do we know that there's even a nucleus? Somebody once took a piece of paper and they started shredding it into tiny little bits and eventually they got down to a nucleus. Yeah. How big is a nucleus? Ballpark. It does depend on the atom, but
Smaller than an atom?
yes, I will agree with that. It's roughly on the order of what's called a femtometer. It's roughly on the order of 10 to the negative 15th meters. So it's tiny. So that's for the nucleus. The atom, really roughly, and it really depends on which type of atom it is, on the order of 10 to the negative 10th meters, just to give you some sense. So notice that the atom is 100,000 times bigger than the nucleus. But at one time they didn't know that. They had this, they were trying to figure out what goes into it, and they had what was known as the Plum pudding model. They realized it was made up of positive and negative charges, and they had this idea that there was just basically this sea of positive charge. They didn't know about protons yet. The sea of positive charge with electrons sprinkled in it, and it's like raisins in plum pudding. I'm assuming that I've never actually had plum pudding. This is just what I'm sort of regurgitating from what was told to me. So in this model, in the 19th century, you have an atom with electrons sort of dotted throughout. And then comes along, and now imagine it was speculated. It always makes it sound like Rutherford went in there to do an experiment and was surprised by what he got. Presumably, he had some sense of what he was going to get before he tried it. But what he did is he took an alpha particle, which is a bit of radiation that comes off of some sort of decay process. And well, we now know that the alpha particle is just the helium nucleus. And he shot it at gold foil. So he had this foil right here, and he shot this helium nucleus at it. Now, in the plum pudding model, if you've just basically got this goop of positive charge, occasionally it's going to hit an electron, you would expect this thing to pretty much go straight through. It might deflect some, but you really would not expect much more than that. And then when it hit, because the electrons are tiny. To give you some sense of scale here, mass of an electron, so mass of the electron is 9.1 times 10 to the negative 31st kilograms. That's the mass of an electron. The mass of the alpha particle is 4 is about roughly 6.8 times 10 to the negative 27 kilograms. So almost 10,000 times more massive. Let's see, an equivalent would be a car and this. If you had a whole bunch of these lined up and a car hit them, yes, it would do damage to the car, but the car is not going to deflect a whole lot if it hits one of these things.
What is that, the mass of the second?
Mass of the alpha particle, that's an alpha down there. Make it more like an alpha. So he sets up this experiment and then sends his graduate students in there to run the experiment. In what potentially is one of the most tedious experiments, because they didn't really have detectors at the time. What they had was, you have this charged particle that would hit a surface and a tiny light would shine. And so you basically are looking through a viewer and you're counting these dots, these dots that will light up. One of the grad students who was working on this was a guy, you probably heard of Geigers and the Geiger counter. This is the kind of thing that would inspire you to actually create a detector to be able to find radiation hits. And what they found was, you know, a lot of the helium nucleuses would hit somewhere around here. But then as they worked their way around, they actually found occasionally some of these helium nuclei would bounce backwards. So imagine you were shooting something that is about 10,000 times larger than what you think you're hitting, and occasionally it causes it to bounce backwards. So you're driving a car along, somebody throws this in front of you, and suddenly your car bounces backwards. This is the type of perception that some people would have from this. And from this, he realized that helium nucleus, because momentum is conserved, has to be hitting something massive. And so with calculations, you then start to narrow down, you get those sort of scale of how big the nucleus is. But he does realize that there is a nucleus to the atom. I don't think they had the neutrons yet. I think that there's another couple decades before they realize neutrons exist. And so then you get into, well, what then becomes the orbital model. So you have a nucleus here with protons and neutrons, electrons zipping around. Sort of like a planetary model. The initial picture was that these electrons would be orbiting. Eventually that changes when they realize that when quantum physics comes into it, so you basically get the quantum model, and you realize electrons aren't really orbiting, you just have probabilities. There's the highest probability that an electron will be here, or at this energy level, but there's some probability the electron will be someplace else. And you can, suddenly that will eventually lead into things like quantum tunneling, where an electron could suddenly appear that you think is on one side of a wall, could suddenly appear on the other side of a wall. And then you get into microscopes that do this, the tunneling electron microscope, based on that principle. All right, just some side notes. Now, as we look at the periodic table over there, you will notice a whole bunch of letters up here. I assume everyone in here has seen the periodic table and at least gone over some of it. The numbers, or the letters, this is the chemical symbol. Then we have a number here and a number down here. What are those numbers?
Atomic number and how many electrons?
No.
The bottom number is the atomic mass.
Okay.
Yeah.
And the top number, the atomic number. What does the atomic number tell you?
I thought it was electrons. And that and electrons.
So you said that and electrons.
I thought the atomic number was also like the amount of electrons in the electron cloud.
It depends, not necessarily.
No?
It's the number of electrons and protons.
The combination?
Well, shouldn't the protons and the electron, no, they don't. Electrons do not always equal the number of protons.
And that's why it's not the number of electrons,
Oh, okay.
necessarily. So,
So it's the number of protons.
yeah.
Oh.
So the atomic number tells you number of protons. So I just pointed at cobalt there. So I have cobalt 27. And this tells us I have 27 protons. That's what determines what the atom is, what type of element it is the number of protons. If there's only one only one proton in the nucleus, it is a hydrogen atom. It will not be something else. Realize that the number of protons determines it. So if I take lead, which is, there we go, lead right here, if I can somehow knock 3 protons out of the nucleus, I can create gold. It is possible. But the cost would be far more than you would ever get out of it, other than just satisfaction of turning lead into gold. I doubt if you'd get much funding for doing that, though. All right, so the number at the bottom, the atomic mass. So again, cobalt, 58.93320. Atomic mass, this is atomic number. What does the atomic mass tell us? You could just go for the simplest answer. Think about the words.
The mass of the, what do you call it?
Atom?
Yeah.
Yeah, okay. Atomic mass does tell you the mass of the atom. Now, the tricky part is, what are the units? So in this case right here, I have 58.9332, and they had to come up with some system here. So grams is the mass. Well, it's not the mass of a single cobalt atom. Cobalt atom is tiny. So the question is, how many cobalt atoms do I need in order to get to that mass? Oh. Anyone?
27.
Is it
27.
No. Far more than that.
She said
I don't know, I just put a 9 over there. I said 9 just because it's in the 9th.
Oh, the 9th column?
Yeah.
Yeah, no, it's more than that.
36.
No, it's way higher.
100.
Really?
Yeah. Cobalt atoms, again, are tiny.
Gazillion.
So zillion? If we could define zillion, let's see. So instead of, who has had chemistry before? Remember the word mole?
Oh, yeah. Avogadro's number.
That's the one.
That's
Yeah,
the one.
so it's a mass of a mole of cobalt atoms. And a mole is just like a dozen is 12. A mole is 6.02 times 10 to the 23rd. Whatever number that is, that's why we do scientific notation, because I'm not sure what that number is. Quintillion? Is that not? Whatever. And so that's what the atomic mass is. Now, there's another advantage to that number is if you round it off to the nearest whole number, so 59, that is a decent approximation for the number of protons and neutrons. I know 27 of those have to be protons, so that tells me the number of neutrons. Doing the fancy math here, 59 minus 27 gives me 32. On average, there's going to be 32 neutrons in a cobalt atom, on average. Sometimes more, sometimes less. So now we get into some vocabulary, because everyone loves vocabulary. Unless you have to spell it. Sorry, for checking. So, if the average number of neutrons is 32, suppose I had a cobalt atom, I'll put a little 58 over here. This tells me the atomic atomic mass for this particular atom. Well, it's cobalt, so how many protons are there?
27.
Yep, because that's not going to change as long as it's cobalt. It's 27 protons. So I have 27 protons. I have 58 nucleons. That's just the generic term for, I don't care if it's a proton or neutron. It's a big thing sitting in the middle. That's a nucleon. We subtract it. I have 31 neutrons. It's still cobalt. That has not changed. But there is a difference between cobalt with 31 neutrons and cobalt with 32 neutrons. So they came up with a word. Isotope. Isotope is just, you have a different number of neutrons inside. So let's take the hydrogen atom, since these words are often bandied about. Generally, cobalt 58, you would just say cobalt 58. There's not a special word for it, but there is a special word for some of these other ones. So if I take hydrogen, 1, so that means I've got 1 nucleon, and it's got to be a proton. So this is known as hydrogen. Shocking. If I take H2, worded badly. If I have hydrogen with 2 nucleons, how many protons are there?
1.
How many neutrons are there?
1.
This is known as deuterium. That could very well be misspelled. If I have 3 nucleons, how many protons?
1.
How many neutrons? I think somebody just said it.
2.
Okay. This is known as tritium. Tritium is highly radioactive. So a story I was told was that at the Savannah River nuclear site, an environmental group was trying to figure out how much radioactivity was being put out into the water supply there. So they did a sampling of water downstream from the power plant, and they found a higher ratio of tritium than is considered sort of normal. And then somebody did the study where they went upstream, and they also found a higher level of tritium than is normal. So the power plant was not dumping stuff into the water, at least not at that point. I don't know if they're doing it now. So if I take 2 hydrogens and combine it with an oxygen, I get H2O, which is, if I take deuterium, which can be symbolized by the letter D. So taking deuterium and combine it with oxygen, what do we have?
Slightly radioactive water.
No, I don't think deuterium is radioactive. But I could be off on that one. This is known as heavy water. So sometimes especially if you're watching a documentary on making of the atomic bomb, heavy water pops up a lot. And my understanding is that if you drink heavy water, it would taste like water, which I guess is tasteless, or should be. All right, so now, depending on how this stuff is organized, we get to then what we had at the end of class last time. We had the solids, we'll stick with the big three, solids, liquids, and gases. Now, if you're looking at the periodic table, there is usually some sort of color coding that the red ones are the ones that are naturally gases. And we say naturally, this is, at room temperature, the red ones would be gases. The blue ones are naturally at room temperature liquids, and then the rest of them are solids, naturally. Now, you'll also notice down near the bottom here, the UUV, UUT, and so forth. Now, some of these names have changed at this point, so a more recent periodic table would not have these necessarily. But the U stands for one, as in uno. B is, I guess, bi. T, tri. Q, quad. P, penta. H, hexa. S, septa. So basically they're just taking the numbers here. Uno, hecta, or UUH. That's what those are. Those are placeholders till they actually get the name. As I found out, the people who get the name of them are the ones who find them. And you submit it to a committee and they get to approve or disapprove. And they also have the rule that if you submit a name and it is rejected, then you can never submit it again. You get your one chance. Now, in terms of what you can find in nature, basically anything up to uranium. Uranium are the ones that can be found in nature. Once you get past 92, that's all man-made. So a question is, why would you make them? Why would you make a 116, the UUH? Why on earth would anybody make an element? Opening up the speculation.